As Tony said, I think we can take probably a 10-minute recess and charge up on coffee and pastries and that kind of stuff, but I'll introduce myself more fully. I'm Maurice Colpron, also known as Mo, and I'm the head of bedrock geology for the Yukon Geological Survey. So our bread and butter over the years has been to map the geology of Yukon. And I'll talk, after the break, I'll come and present what we've done. I guess we've been doing this for 7 years now. So I'll present all the various aspects of the project, and I'm going to go through this chronologically so that we've learned lessons. We started with knowing very little, if you know, almost nothing about geothermal, but we just said, well, we're geologists, we can figure it out, to a point where now we think we have a reasonable approach to, I think really the research that we're doing is more about de-risking. So it's not so much about, are we looking for a conventional resource or an ever type resource, but even whether it's ever or conventional, whatever, if you can drill and get the heat that you want at 2 kilometers, you're winning rather than drilling 7 kilometers to get it. So I mean, all this is possible. The technology is there, you can do it. But your winning thing is like, the less I have to drill to get to that heat, the better it is. So whichever system we're trying to do. So anyway, without going any further than that, I'll just mention that, so my presentation will summarize a lot of work. In this room here, we have a number of the researchers from universities and other Geological Survey of Canada's and that have collaborated with us in doing this. So around the room, there's a bunch of posters which kind of provide more detail to the snapshots I'll give. So I won't get into great details with the techniques and all this stuff, but if you want to talk directly with the researchers, they are here. And at the end of my presentation, I'll invite them to come to the podium and introduce themselves so you know who's doing what and who you can talk to. So what, 10, 15 minutes is what? So my task here for the next while, I have quite a bit of material to go through, and I just want to kind of go through, I kind of said that a little bit before the break, but I'll go through the various projects that we've gone through and try to summarize what we've learned from these different projects. I have a fairly long presentation. I wouldn't be surprised if I get interrupted by lunch, and I won't hold you back and keep you starving. When lunch starts up, maybe we'll take a break and I can finish after that if I don't get to it before we get to lunch. So as Carolyn said, you know, 2016 is really when we started getting in that game, and it was sort of about, you know, how can we contribute to this green transition or the green economy, I think, or green energy transition. How could we address some of the goals of the government for reducing greenhouse gases? So being geologists, then, you know, anything that starts by geo is kind of interesting to us. So we said, well, we can probably play in that geothermal space. So that was great, except that we had no experience with this other than, yeah, we know the basics and we can figure that out as geologists and scientists. So we did kind of engage with people like Jeff Witter, who spoke already a few times, has worked a fair bit with us, and Steve Grasby that Carolyn mentioned earlier, who's a colleague from the Geological Survey of Canada in Calgary, and probably the main expert in Canada these days. So on their good advice, we sort of kind of slowly ramped up our activity. So why geothermal in Yukon? About the time that we were doing this, I think it was the what's now called the energy branch of Energy Mines and Resources. So they're better known as the Energy Solution Center. That's where you get your rebate when you get a Energy Star dryer or something like that. But they had commissioned the Canadian Geothermal Association, which is a Calgary-based group, to basically compile what do we know about geothermal energy and what are the opportunities in Yukon. So there's a report that I don't know if it's printed here. If not, it's available through our website. There's a report they produce, but it's really a cataloging, and one of the highlights of that report is how little do we know, how little data do we have to derive these this kind of interpretation where the good spots are. So, this is kind of an amalgamation of my own distilling some information from their report. But those yellow and red areas are areas that they deem, well, they're probably okay, and you probably should look more into that. A lot of the rest of the report is about how it could be used in various communities. So there's a useful information of what might be potential use of geothermal resource. The more scientific reason is this other graph here, and I'm not going to get too deep in this, but this other graph came from very more kind of crustal scale, like trying to understand the whole evolution of the northern part, the northern Cordillera, the northern mountains of Western Canada, and they kind of found that orange box here. That's us in Yukon. They found that the heat flow, so how much heat comes out of the crust in the northern Cordillera, is significantly higher than that red bar, which is the average North American value. So we said, oh, okay, that's interesting. We have elevated heat flow, so maybe we have opportunity for geothermal. I did say on that slide that this was based on very little data, and the same with the CanGeo report. So when you compare that heat flow, this is a map from the same report. I've just kind of splashed up everything that is in that 100 heat flow value in red there. But when you compare to the Great Basin of the southwest U.S., western U.S., you can see that a lot of our values, 100 milliwatt per square meters, average 100 and 105, but they're comparable to some of those hotspots in Nevada. And if you've driven around northern Nevada, you go about every 20 to 50 kilometers, you'll pass a geothermal power plant. So they're producing a lot of power. Jeff is working with projects there in Nevada as well, and so we say, well, maybe Yukon can do that too. But the recognition is that our data set is not quite up to snuff. I think on that map of Nevada, every little splash of black is a drill hole that they've used to produce that modeling. We're nowhere near having that kind of drilling level here. I won't go into the details of this. Carolyn covered these different, but what do we look for when we're trying to assess an area that would be interesting? We're looking to see whether we fit into any one of these n-member model that Carolyn already discussed. Ideally, you want to get, I think Nevada, most producing wells are in the 1.5 to 2 kilometer depth. So if you can get that heat, so if you want to produce conventional electricity, you're talking about 120 degree high and higher. You want to get that heat, and then ideally you'd like to find it within 2 kilometers. Doesn't mean you can't go deeper and tap it, but it's going to cost you more money. And so if you're trying to do this in that 2 kilometer boundary, you're talking about a geothermal gradient. So how much increase of heat as you go down the earth? You're talking about 60 degree C per kilometer to get to that 120 degree at about 2 kilometers. All this being said, everything lower is still useful. We can do stuff with that. It may not be producing electricity, or it might be a little more complicated system like what Carolyn talked about, Chena Hot Spring. That's still possible, but Chena doesn't produce a huge amount of power. It produces enough for that little resort. But that kind of stuff might be suitable for some small communities if it can be done cheaply enough. So in order to do this, our approach is we need to understand what the subsurface is, and there's various techniques we've used to try to understand the geology beneath our feet. And then ultimately you want to find rocks or features in the crust that will allow the flow of hot fluids closer to surface. And so a lot of the stuff that we're doing and that we have done and we're doing is trying to answer those questions. So when we started, again, I said we were pretty green about that, and that's pun intended. So we're in Whitehorse. Carolyn mentioned it. We're on the edge of Whitehorse Trough, and this is where that map shows the different transmission lines. So that's where the power grid, and we were pretty much focused on trying, well, where's the opportunity for finding power? So we contracted Jeff to do a bit of a desktop exercise to look at where are opportunities near roads and power line where we should kind of look at that. And that's these different polygons there and trying to match those end member model. But another thing that came out of it was a recommendation for what other easy things could we do to, before we drill, before we go anywhere, to sort of zero in to where would be the good spots for geothermal. So, and those are the two things listed at the bottom: the Curry point depth mapping, and I'll explain that in a minute, and the radiogenic heat calculations is another things that those were easy desktop things we could do without leaving the office. So the Curry point depth mapping is really it's using existing data. So the map that I'm showing here is the coverage of aeromagnetic data. So that's over the years between us and the Geological Survey Canada, we've covered pretty much all of Yukon. The only blank spot is the High St. Elias, where there's all sort of reasons why it's a national park, first of all, but it's mostly the rugged mountain and high topography are not practical to do that kind of collection of data. It's too remote and too difficult to fly at those altitudes. So this is just done by flying a plane, flying an aircraft. We collect that data. Where it's bright red is where the rocks are really magnetic. Where it's blue is where the rocks are not magnetic. That's the base data. But using that data, and the people who can explain that in great details are sitting in the room. I'm not physicist in any way, but we can calculate from that data the point at which we demagnetize, where the rock lose that magnetization. That's a temperature of about 580 degrees. So we're measuring a point relatively deep in the crust, but if we can map where that demagnetization is, that might give us a proxy where 120 degrees would be closer to surface. So we did that. And this is the result. So this is what we call the Curry point depth map, and it will come back in various points in my presentation. But basically, warmer colors are where that 580 degree demagnetization is closer to surface, and the cooler color is where it's deeper. So if we look at north of that Dawson Fault, so the Peel River area, for example, the Peel River watershed, it's pretty much blue, and that tells us that in order to hit 580 degree, we have to go down to something like 40 kilometers. So it's way down there. On the other hand, once we look, in that southern Yukon around the Denali Fault, it gets up to 12 or 10 kilometers from surface. So those are areas where we should expect that 120 degree would be closer to surface. So that's been a guide, but this is all the guys who do the physics that are sitting in the back of the room here, they will tell you this is that's really sketchy. You can't. So this is the first order tool that we've been using, with the caveat that we knew, well, it might be wrong. It may not tell us the right answer. But it still was sort of a guideline to go. The other thing was this radiogenic heat production. So Carolyn talked about that. Granites of certain composition have radioactive elements in them that can produce heat. Now, I should qualify this that by radioactive, this is not human health problem kind of radioactivity. It's a very low level radioactivity, but it's enough for these elements to potentially at a few kilometers depth produce enough heat to warm the water. So this was an easy thing to do because, as I mentioned, our bread and butter is to do bedrock mapping. So when we map, we could sample the rocks so that we can do lab analyses so we understand better what those rocks are. We're trying to understand, what their age and whatnot, what their composition. And with that, so we had already a ready available data set of rock chemistry. And all we needed to do is just put them all together and put them to an equation to calculate how much heat they could produce. So your average granite would usually produce 2.5 to 2.8. We can, it's microwatts per cubic meter, but let's just use the numbers for now. That's just a baseline. 2.5, 2.8, it's normal, it's the average stuff. So it doesn't produce that much heat. Everything that's above that, and we have a lot of those in Yukon, everything above that is anomalous and has a potential to heat the rocks or the water if water flows through them. So, and we can notice that there are high spots, like, the Tombstone Mountains have high, and they've been known in the past. There's the uranium is so high there in some case that they were explored way back when for uranium. So there are uranium minerals. Other places we don't necessarily have uranium as a resource that we could extract, but there's enough heat still produced in those rock. And I'll talk a little more about the Seagull Suite because that interested us because it's close to the highway and whatnot. So that's by Swift River. So those were two things that we did right off the get-go. So then the next steps are, okay, now let's use these tools to try to target and see, okay, let's go, where can we find things? Where can we find a potential resource? And of course, heat doesn't travel very well. So you can't find heat 50 kilometers away from here, put in a pipe and say, I'm going to use it in Whitehorse. By the time it gets here, it'll probably be 20 degrees or like you'll lose a lot of heat. So it's something that has to be, if you want to use that heat, to be pretty close, if not in your community. So we've taken an approach to say, okay, now let's look at communities where or try to identify what opportunities might exist in the geology. And our tool was to develop these 3D geological models. So we map the bedrock surface so this is sort of a three-dimensional view at an angle, if you will. That's always hard to see these things as static. But the top is the map that we produced, that we walk on the ground, map the rocks, and understand that. That other slice there is a cross section, so you'll see that, and Carolyn has presented some of that. We like to do this as geologists. We like to visualize, if we slice the earth and look through it, what should we expect to see? So these are models, like, but there are guidelines as to where should we go. And so to build this stuff, we're using the bedrock map, and we're using a whole range of geophysical studies. And then the ultimate test is when we can drill through it and see, is our model really meeting reality? So I'll go quickly to these various methods. So here I took a snapshot. This is the bedrock geology map around Takini Hot Spring. So Takini Hot Spring, obviously that's an interesting spot. There's water at 46 degrees coming out in a pool there. So there's that. We have a granite just west of it. Yeah, that could probably produce heat to heat that water. We look at the different rocks. There are rocks that, from what Carolyn showed, there's rocks that have a potential to have porosity so that the water could flow through them. There's limestone in there. The limestone, they easily dissolve, and they form caves and things like that. So that could be area where the water could pool up and form a bit of a reservoir. And then the other feature on this map is fault. So the main one is running through here. So a fault is just a break in the rocks. It's pretty obvious here because you can see, what we like to do as geologists, we color the rocks. There are different units or different colors, just tells us about the composition. It's a visual way for us to represent what the different composition are, different ages of the rocks and whatnot. But you can see that there's a north-south fault that runs right east of the hot spring proper. And so that potentially could be a channel, a plumbing system in which water could come. So that's one layer, the bedrock geology. We fly airborne magnetics. I showed the map for the whole Yukon. This is usually done by helicopter or fixed wing aircraft that flies over land. And they produce a map like this with all these various colors that I mentioned already. And that's useful for us to identify different rock bodies, and we can identify boundaries between rock bodies using this kind of approach. Another thing that we've done, that we're doing and have done and are doing more systematically, particularly focused on communities, and I'll talk a fair bit about this method, the gravity surveys. All these methods, I think it's mentioned in there, they're all passive. So we're not doing anything to the ground. We're just reading what the ground has to tell us. So with the gravity survey, we're measuring the different densities of rocks. So different rocks have different weight, and we can put that instrument on the ground, and it gives us an approximation of the difference in weights across the area. So if we have a limestone, that's a fairly light rock. If we have a basalt, that's a pretty heavy rock. So we can sort of measure these properties in the rocks using this gravity survey. The image at the bottom just show what this looks like. You'll notice that we like to always present all sorts of different data, and they're always these red to blue colored thing. This is just a way of showing where the rocks are red, they're denser in this case, and where they're blue, they're lighter. So another method there's a variety of method that we call electromagnetic. So they're just measuring how electricity conducts through the rocks in combination with their magnetism. So it's a bit of a hybrid to that aeromag technique I talked about. And in this case, we install an instrument for 1 or 2 days, and we're just using natural source like lightning or auroras. They're producing the electrical field, and we're just reading how that electrical field interacts with the rock bodies, and that again gives us different, help us identify different properties in the rocks in the subsurface, and in this case, we measure either the rocks are resistive or they're conductive. So what in geothermal sense, what we want to find is where they're conductive. So it is where electricity flows better to the rocks is a good indication, because if we had a saline brine, if we are at 4 kilometers and we have that deep formational water, that usually will be full of salt, and it will conduct electricity better than just plain water or plain rock. So, and then the last geophysical technique that we're using is passive seismic technique. So we're relying on, generally the methods that are being used will measure very, very small earthquakes, like very things that are probably happening right now under our feet and we don't know. And so with these very sensitive instruments, then we can use, and so the seismic earthquake is the same thing. So earthquakes will travel through different rock bodies at different speed. So, and that's the minute things that we want to measure in this. It's like by measuring how fast it goes, then we might be able to identify the boundaries between two rock bodies, or we might be able to identify different rock layers in the subsurface. So we want to combine all of this to help us kind of get a picture of what the geology is in the subsurface. The last line is basically also, of course, the seismic methods are useful for hazard, because we're measuring earthquakes. So it can tell us, even by detecting small, very minute earthquake, it might help us pinpoint where bigger earthquakes might occur in the future. So it has double or multiple use. And then the ultimate goal is to drill. But drilling is a complex activity. It's expensive. And if you don't drill at the right place, it's a lot of money to not get the answer that you want to get. So this is always the the last thing we want to do. We've not always done that, as I'll progress in the presentation here. The map that's shown here is a compilation of deep wells, or wells where we actually got temperature information. And I'll come back to this map and I'll talk a little more about that. But of course, where do we have the most drilling with information? Is the old oil and gas basin, Eagle Plain, the Yard Basin in the southeast. Those areas have been drilled extensively for oil and gas back. A lot of this activity was probably back in the 60s, 70s. But that ultimately is giving you a direct observation of what's going on the subsurface and a direct measurement of temperature. Okay, so over the last, 7 years now, 6-7 years, we've conducted various research. I talked about the desktop exercise. Now I'll kind of go through the focus studies that we've done. And I'll go chronologically. So we started Takini Hot Spring, low-hanging fruit, just right outside here. There's hot water coming out there. And then we went through all these communities, and we're keeping, the work is ongoing. We're not done with this stuff. And then toward the end, I'll talk about what I call the opportunistic studies, is where this is not work that we first generated, but we entered in collaboration, or were able to access some of the information that was done either from mineral exploration, or Eric talked about the Ever Yukon project near Carmack. So we did partner with Ever on this, and also I'll summarize some of the results we've seen from that. So Takini Hot Spring was the first thing we did. We said, well, let's go to Takini Hot Spring, and we decided, well, let's go drill and see what's going on. Why is there hot water there, and all that stuff. So we partnered with Tom Cochan on accessing a site on the old Sawmill Road on their Category A land, and got a drilling project going on there. We knew we were going to drill at the edge of the Whitehorse Trough. So Whitehorse Trough is a basin that has potential for oil and gas. So we approached that drilling with caution, because we said, well, we're not drilling for oil and gas, but we have to be ready in case. So this was technically, there was a challenge there. So we drilled down to 500 meter, and that's the temperature profile we got there. So we got, this is the first time we did this. We installed a thermistor cable. We had put a bead, a thermistor, every 50 meters down that cable. We installed it for 6 months and let it equilibrate, and that's the equilibrated temperature is presented here. And we can see that it's 16, 17 degrees. It's below average, which is 25 degrees C per kilometer. So if we wanted to hit 120 degree at that particular location, we'd have to go quite a ways. So it's not a really exciting target, just in terms of geothermal gradient. But at the bottom, the last bead that we had just spiked to 25 degrees. And unfortunately, because we designed that thermistor string the way we didn't have much information as to how sharp, is that gradual? We don't, so we're limited in the information to understand exactly why it spiked at the bottom. We lost the well, we couldn't go any deeper. There was no opportunity to re-enter it because of complication in the drilling. And we didn't get a chance to actually sample the water, so we lost a chance of getting information about the water. So this was our first experience. We did that. So I said there's many remaining questions, but despite that, we had core. We were able to look at the rocks, understand a bit better the geology, and Jasmin Raymond here is going to speak after lunch, and his group, they still generated a bit of conceptual model. There's lots of caveat in that model, but going back to that map I showed several slides ago, we know that there's a granite, and we know from our desktop study that it has above average heat production value. So we're at this point, we think that the interpretation is that the granite probably heats that water at Takini Hot Spring. And it's probably flowing through these rocks and hitting that fault that's around Takini probably helps channeling that water near surface and bringing it up to the hot spring. So this is where we're at. There's more work to be done to really understand the story there. After that, this is a somewhat of an opportunistic study because we piggybacked on some work that was done in 2013, 2014, and Jeff here was involved with that program. And this was work commissioned by the Ross River Denuk Council in collaboration with the Barclay Group and Mira Geoscience, who was employing Jeff at the time. And so they went in there and evaluated the Tintina fault zone, the Tintina Trench near Ross River for potential geothermal sites. So they got access to industry detailed aeromagnetic data. The map shows where we did MT data, that magnetotelluric, which we will refer as MT, it's less of a mouthful. And the idea was to test this kind of pull apart type situation in a fault, like Carolyn explained earlier today. So there was already a lot of groundwork there. We had budget to do more drilling just after Takini. So we entered in a discussion with RDC and said, like, hey, we can, what the work that Mira Geoscience and Jeff had done identified drilling, but they didn't have budget for drilling. So we came in and said, well, we're willing to partner and follow up on this and test at least one of those sites. This shows some of the highlights. So on the map, the magnetic data show that there were north-south structures in the Tintina fault zone, which might be amenable to opening cracks and allowing water to the surface. This block diagram, this little 3D model there is the MT data that was acquired there, and that blue blob was we guessed that this might be a buried pluton, so it might be a buried intrusion, potential source of heat. So this is where what their work had done. That's where they were left. We went in with brought some budget to drill along the Canal Road, just on the south side of the Campbell Highway. And we went down to 484 meters, had a lot of difficulty in that drilling. It was -40 pretty much through the whole drilling program, which didn't make it easy. Again, we installed a thermistor cable, but we got a little smarter with it. So we spaced our thermistor a little. We put more thermistor in the cable, got a little better resolution data. And there we were measuring about 31 degrees C per kilometer. So that's above the average 25 degrees C per kilometer. So not hot, but it's somewhat abnormal. So there's opportunity to get some water of some heat without drilling super deep, but it's still far below that 60 degrees C per kilometer that we'd like to hit if we wanted to do electricity at about 2 kilometers. So then in 2020, 2021, we put in a proposal to NRCan on their emerging renewable power program to evaluate fault control geothermal systems specifically. That's a program that they had that evaluate. They've got different projects evaluating geothermal potential in various parts of Canada, in BC and Saskatchewan and Alberta. But nobody was evaluating this kind of target. And we said, well, we got great big faults in Yukon, so maybe we put a program. So we received $2 million of funding from those guys. And that was supplemented by the Clean Future initiative of YG. So we basically had about $3 million to play with for the last 3 or 4 years, and that brought in that brought focus to projects in Burwash Landing, Teslin, and Watson Lake, which I'll talk about next. And this, a lot of our collaborators that are here in the rooms got involved with us at this stage of the project. And then we started kind of trying to apply more that approach of multiple geophysical methods combined with bedrock geology and whatnot. So the place to date where we've done the most amount of work is the Burwash Landing area. And we went in because, well, the Denali Fault is an active fault. We all know that from May 1st, 2017. We all woke up at 5:18 because the faults related to the Denali were shaking that day. So we said, okay, if there's an active fault, so we might, as was explained earlier, there might be a chance to keep the conduits open because they keep moving a little bit. And then the other piece of information, KFN, Kiwani First Nation, had drilled in, I think, 2012 or something like that. They drilled down to 387 meter in the community. And they had water at the bottom of that well was 17 degrees. So if you do the back of the envelope calculation, that gives you about 45 degrees C per kilometer. So, okay, that's elevated. I've been signed out because my account is, we'll see what that means. And then the other thing that we were looking at is I'm signed out. I didn't pay my bill. Everything should be good. Okay, perfect. So we went there because there's hot water. We're in Denali Fault, which is active. That Curry Point depth mapping exercise that we did early on is pretty hot. There's shallow Curry Point depth, about 14 kilometers in beneath Burwash Landing. And when we look at the geology map, what I've just highlighted there is that right around Burwash Landing, the mapping of the Denali Fault that we have shows that there's multiple strands of the fault, and that is suggestive that we might be in a situation where we would have one of these pull apart, which would allow opening space in the fault zone. So to test that, we did this gravity survey. The ELF survey, it's one of these electromagnetic survey, but it's a ground survey. It's very similar to the gravity. It's just an instrument that's left on the ground and measure the passive response. So we got these results. The map on the left is that ELF electromagnetic survey. And lo and behold, just by the Duke River, we see a kink where it's highlighted. It's surrounded by a white ellipse there. There's a kink in that fault that is kind of, okay, well, maybe there is a pull apart zone there. The images on the right are two sections through this electromagnetic, so they're vertical slice projected, and then we can see that's bright red is a conductive zone around the Denali Fault, and there's a bright red finger that comes almost to surface at that site. So using that data, we decided maybe we should drill here. So that's the plan that we put in together. We were working on this with KFN and discussed the area and make sure that this would be a suitable area to do this. And then before we actually got to drilling, we decided we'll do more of that, we'll throw more geophysics. So we did an empty survey, which like this, the map shows a bunch of dots, is where we installed all these various instruments. We did an empty survey. We applied some passive seismic methods. The right-hand side shows both a map view and a cross-section of the MT. And it just shows that these conductive zones have a potential to go quite deep in the crust. So this is about 8 kilometers of crustal section of thickness that we're looking down here. So we were quite encouraged by this material, by these results. The seismic data is like, most of that data was collected in the last year, so it's still being processed. We haven't quite got the advantage, but we had the money for drilling, so we went ahead and drilled last winter. And then we drilled, again, we've had complication. We didn't get very far in our drilling. We only got to 220 meters at the Duke River site, but we still have hope. We have this well left in a situation where we can re-enter and go deeper, and we're seeking funding right now to finalize that part of the project. So the Duke River, that red profile is what we've measured. In that case, now we had learned by then that really the way to go is to measure continuous temperature profile, so that if there's anything happens, we can see what happened. So in this case, we installed a fiber optic cable and cemented it in the well. So, and then we went back, I think it was June. So we had to, this was done last November, the installation. We had to let it sit there because, cement actually generates heat. So we had to wait until the cement is properly cured. So we're not reading the temperature of the cement, but the temperature of the ground. So we did this in June. And that's the profile we got. So we're at 37 degrees C per kilometer, and this is measured mostly in rocks. We hit bedrock at about 49 meters, so most of that is bedrock reading. But it's a short segment, so we'd love to have a much deeper segment to really know whether that's what's going on there, or is that going to project further. So again, here we're more elevated. This is a little lower than what the back of the envelope calculation we could do for Burwash Landing. The well at the bottom is another continuous temperature reading that we took in the well in Burwash Landing, and in that area we got 49 degrees per kilometer. So that's kind of interesting. The issue with the well at Burwash Landing is it's entirely in sediment. So it's entirely in glacial sediment. So it's not consolidated rocks. And traditionally, the heat conduction in those rocks is not reliable to measure a crustal geothermal gradient. So Jasmin and his group did other tests, and they will be on a poster around here, and he can talk more in detail about those measurements. But in both cases, we're getting, comparable, at the bottom lines, there are these heat flow values. So 116, 110 at Duke River, 99 so it's in the ballpark. It's equivalent heat flow at Burwash. So it's encouraging that there is potential for warm water, but we're still below that 60 degrees C that we would like to see for a shallow geothermal resource. Okay, we're doing a whole bunch of other things, and the results are start coming in. So this is one, it's kind of one of the interesting one is this is a LiDAR survey that was acquired just before we started this project. It wasn't us that acquired that, but we ended up partnering with the group at University of Northern British Columbia, who was acquired that survey. But and then we have a PhD student at UVic who's actually working on sorting out the details from that data. But you can clearly see the Denali fault. It says that main fault there. There's a scarp that runs through the landscape. It comes up on the other side of the Duke River. The various colors are various age of fluvial sediments, so the river sediments through the age, and the students working on that is now trying to date those various. So the various colors are like the dark brown is the youngest river sediments, and then the pinkish color and gray color are the older sediments. So they've sampled those rocks to try to date them by carbon dating. And it's because some of the sediments are seeing effects of the fault, whereas the youngest one are not seeing effect from the fault. So we're trying to bracket when was the last earthquake on the Denali fault near Burwash Landing. And then the other interesting feature is that even in that data, he's got that 7-degree releasing bend labeled there. So we see that jog in the fault we had hypothesized originally, but now we're seeing it in multiple data sets. It always shows up. So I think we're quite confident now that, yeah, there's a jog and default at that area. So I'm listing other things. So out of this, there's a PhD student that's working on modeling the hydrothermal flow, and with all the data that we've so she did those temperature gradients. She did a heat injection test in different wells so that there's better understanding of heat flow in those areas. But with all of this layers of geophysics we have, I think it's going to be a quite exciting study when she finished that, just to understand the 3D model in the general area. We've done some field work looking at the Denali Fault proper with colleagues from USGS. We've sampled water chemistry. We're analyzing that. Steve Grasby, who couldn't be here today, was just here about 10 days ago collecting shallow temperature probes. So they were just installed about 50 centimeters in the ground, just to see what kind of heat is radiating. And so that's a really cheap method we can do, and they're just analyzing that data now. So we don't have any result to show. And then there's a lot of different seismic data that was collected. There's two of our colleagues from University of Calgary here that can talk more about that data. It's early days. We still, some of the early results, for example, we can use the earthquake data to map the depth of that sediment layer that covers the area around Burwash Landing. So now we have a better estimate of how deep we have to go before we hit bedrock in those areas. So that's one of the byproduct of this seismic work. Okay, so then we went on to Watson Lake. We did a project there. And so what led us to Watson Lake was basically, again, was kind of a continuation of what we started at Ross River. But in that area, there was not, no data like we did for Ross River. So we designed a program to address that. There was indication, I think, there's just at the edge of the slide, there's a green dot with 49 on it. There was indication from one nearby, and this, by nearby, I'm saying this is 30 kilometers east of Watson Lake. There was one deep oil and gas well from the 60s that reported a temperature gradient of 49 degrees C per kilometer. So, okay, maybe there's something. But once we look into that data, we don't really have confidence in what that is. All they did is measure the bottom hole temperature. And there's no, we don't have that profile to go on. So it's just like, assume it's 0 at surface. It's it's 49 degrees at 1 kilometer. That's the temperature gradient, which is not an ideal way of doing it. So it's a low confidence gradient. There's another one, but that's a very shallow well that was done at Watson Lake, and we got 20 degrees C per kilometer there. But I think that well, don't forget, I don't remember how deep it is, but it's 100 meters or something like that. So it's too shallow to be useful as well. So we don't have much information about that. But we're in the Tintina Fault Zone. That broad fault zone that basically goes from Highway 37 to Watson Lake proper is filled with young sediment. By young, I mean 50 million years old. I deal with hundreds of millions of years. But this is a younger basin that suggests to us that there might have been some opening and extension in the area. So in order to, and then the other component in that is that there are quaternary basalt. There are young basalts. Like if you drive, like the most obvious exposure of it is at Rancheria, which is quite a bit further west, but it's the same occurrence. But if you come out of the Rancheria Valley, you'll notice there's outcrops of basalt sitting right there, that this kind of brown rock is sitting on the side of the highway. So they are throughout the area. But they are, I think the youngest dated basalts are like 250,000 years. So it's unlikely that they're producing heat themselves, because they would have cooled way a long time ago. So this wouldn't be an Iceland type situation, but it's an indication that there might be some heat source. And that they may actually also promote opening some space as they came up to the crust. So those were all elements we looked at and said, okay. So we got into collaboration with Liard First Nation on that project. They brought in, I think Carolyn mentioned that in her presentation, we put some money into the project, and they were able to raise additional money to do some of the work in the area. And then the main work that we did there was gravity and MT surveys. So the gravity is in that blue box, is where we acquired the data, and all those triangles is where those instruments for magnetotellurics were installed. And then we also had some seismic instruments deployed in the region. They were recovered, I think, sometime this summer, end of summer or something like that. So the data is in processing. We don't have anything to report about the seismic, but there's data coming. The gravity and MT, and there was, we also had a relatively recent aeromagnetic coverage that's fairly detailed that we were able to analyze. So the map in the corners, the magnetic, one thing that's really good at showing us is where those basalt exposures are, because you know when you drive around, it's the Liard Plain. You drive around Watson Lake, there's not much rock to look at. There are a few exposures here and there, but that helps us identify areas where we didn't know there was basalt, but just by looking at the patterns on the magnetic map, we can identify more of the basalts. The lower right is a cross-section through that magnetic. And so if you notice where it's, the Tintina fault is drawn here on this map, on the left, there's a really bright red spot that's a magnetic high. So we know there's a very magnetic rock. When we model it in cross-section, we come to the conclusion that there's probably another one of these buried plutons. Same thing that we suspected with different data set, but same thing that we suspected at Ross River, but it's at 4 or 5 kilometers depth. So and we don't know what it is. So, but that might be one of these heat-producing plutons. There's a chance that that might do that. The map in the low upper right is the gravity data that we collected, and one of the first thing that, because there's no exposure in this, where the Tintina fault was drawn was really a guess. It was sort of like, it was a guesstimate that was done by squinting and trying, it probably goes through there. Now we have much better data. We know that now the Tintina fault is almost at junction 37, not in the middle of the blue as it was shown by this dash line there. So we got that incrementally getting better information about the geology in the area. The MT survey was quite interesting, is quite interesting, but it's puzzling. We're still debating what that really means. But so the top diagram here is a cross section, is one of these slices through the MT modeling. And then you can see that there's a very bright red zone that goes from almost Watson Lake, or just west of Watson Lake, to Highway 37. This is this kind of red and brown and yellows, sits flat there. So when we see this, the first thing you ask is, well, that could be those brines. Maybe there's a lot of brines underneath this area. But the other way that we can do this is by, the mineral graphite, which is common in shale, is a really strong conductor as well. So, and then when we look at the geology in the area, there are multiple rock units that are shale, that are black shales. So they're shale full of graphite. So our conservative guess is that, and the other thing is that this is, I don't have the scale in kilometers here, but this is tens of kilometers of this conductive material, and it occurs beneath those 50 million year old sediments. So we don't see ever what those rocks are. So that's why it's labeled unknown rock type. So one possibility is it would be hydrothermal fluid or geothermal fluids. The other possibility, which we're kind of leaning, is probably the more realistic scenario, is that this is one of these units of black shale that's buried down there. So the only way to really test this would be to drill it. And I think there's on the slide here, there's a white bar that's a proposed drilling location. And that's one way where we could get to sample what that conductive zone at the shallowest depth. So without drilling, very, very deep, we might get some information about what it is. So, but right now, and also all the other information, from that oil and gas well and some mineral exploration work that was done in the area suggests that the rocks that were encountered are not very permeable. So even if this was a brine and a geothermal fluid, we're unsure that you would be able to flow water sufficiently to produce either heat or electricity to a good. Now we're lacking. We have no direct idea of what the geothermal gradient is in the area. So drilling a well will also get us that information, and so that's where we're left with the Watson Lake. We've identified one drill target, and then the bottom is just showing this 3D geological model that we're always trying to build for various areas we're going into. Is the lunch on the table? So, okay, after lunch we'll go to Teslin. All right, so I'll move on with Teslin. This is the last community where we've done a fair bit of work, so everything else should go pretty fast after that. There's going to be short things. So, what attracted us to Teslin? We had this fault control geothermal fault control system. Do we want to evaluate? There is a big fault going through Teslin Lake. So we went there, and just north of Teslin, we also noted that Curry Point depth is relatively shallow. So we targeted that area as being potentially interesting. The other thing that we thought was interesting is in the geology map, there's a bifurcation. The Teslin fault becomes more than one. So that potentially is an interesting area where we might develop these openings between the faults. So we went there, we did the same old stuff, gravity, we did some MT. Just recently, we finished acquiring an airborne survey. So if you're from Teslin, you saw a helicopter flying a few weeks ago. That was an EM airborne survey. And again, we did some of that passive seismic. Not all the data has been received and processed, but we have been working with the existing magnetic data we had and the gravity. And we did find an area around Fox Creek that seems to be promising for opening ground. So that's an area where we would focus, and that's the area where I guess this is in the gravity. Here's a preliminary map of that electromagnetic survey that was flown. And again, we see that same northeast trending right blob there, which suggests that there's conductive rocks in the Fox Creek area. So again, that would be the next step for testing the Teslin area would be to drill. And we would propose to drill somewhere near Fox Creek. The easy drill location that's been identified is actually near the sewage lagoon in Teslin. So that would be an area to go test, see if we have suitable temperature gradient. Now we've also acquired data at Haines Junction. This was done in August. We still have not received that data, so we did gravity and MT data there. And there's been some passive seismic data that's been done there that's also under processing. So this is the story is still to come. So Ray will be talking again to let you know what we're finding there. But we are on our way to build a model for Haines Junction as well. And the latest project that we have, which is slated to start any hour now, as far as I know, is starting to do some geophysics here in Whitehorse, the northern part of Whitehorse. And so this came together because, well, we had funding left this year in our project. And I was talking with our colleagues at Highways and Public Work who are trying to make YG infrastructure more energy efficient, or going toward that net zero goal. With particular emphasis, they're looking at opportunity for Yukon University and that upcoming school in Whistleban, the Whistleban Place, and those buildings down there. We've been talking for the last year or two on and off about this, and I say, hey, why don't we just start doing gravity? So this survey should start, as I said, probably this weekend or any time now. That gravity survey should start, and then so this is the first step. We'll be looking at what else can we do in the future. Whitehorse being the main center of population, it's a bit challenging from some of the other geophysical methods that we use because there's too much cultural noise, there's too much human activity, but we're working on how we're going to advance the Whitehorse area. What's interesting about Whitehorse is it's essentially the same geology as Takini Hot Spring. There are warm spring in Porter Creek, Stinky Lake, Versluis are probably better known, and they're sitting, and there's Pluton. That Hackle Pluton is possibly an equivalent to the Pluton that we that exists just west of Takini Hot Spring. So the type of system that we see at Takini Hot Spring is what we expect we would see in the northern part of Whitehorse. Okay, and I mentioned these opportunistic studies. So those are where exploration work by other folks have happened, and we had the opportunity to collaborate or access some of those infrastructure. One of them was by Swift River, and that sort of came out of that study of radiogenic heat production. And the Plutons just north of Swift River are really hot. So this is a bit more academic because this is far from any community. It's about, as the crow flies, I think it's something like 70 or 80 kilometers east of Teslin. And then, we all know Swift River is 15 or 30 guys that are on a highway camp there. So I don't think it's worth spending hundreds of millions of dollars to develop something there. But it was interesting because those values we're getting there were so hot that it just became a bit of an academic exercise. And we had access because there was exploration. So the map that I'm showing here is a radiometric survey. It's an airborne survey that measures radioactivity. So we had access to that data. So we did a bit of an analysis. We wrote a little paper about that. I think this is a really exciting target. It's just in the middle of nowhere. If ever there was a power line going along the highway there, then that might become in the future something to look at. And that's comparable. I was mentioning in discussion this morning, this project in Cornwall in the UK, where one of the byproduct is lithium, but they are building a power plant there. This is a very similar analogy. This is a very similar setting. That's what's in Cornwall. So somewhere down the future, if a major town grows up out of Ross River, out of Swift River, maybe that will be interesting. The other opportunistic studies, there's a deep well that was drilled by Kloani Drilling here in the Whitehorse Copper Belt, just by Mount Sema. That was revisited by Ever Yukon in partnership with Kloani Drilling. There was some temperature measurement that were taken there down to about 1,100 meters. We re-accessed this with our high precision probe just about a week ago or 10 days ago is when we were there. We only made it down to 650 meters, which is still a respectable depth to actually get a sense of what the geothermal gradient is. It's dead on average. The data that Ever Yukon got was 26 degrees C per kilometer. Ours was 25. So I think that area, as far as getting heat at the reasonable depth, is not high on the list at this stage. And the final, partnership with Yukon. Yukon drilled just outside of Carmax along the Freegold Road, and they went down to about 720 meters. But there's some rotten rock in that well that, by the time they came to measure the temperature, they could only get down to 350 meters. And it's just, there's rocks that are just kind of collapsing back in that hole pretty readily. But we did partner with Yukon. We got access to the core. We did a lot of lab work on analysis to try to understand how heat propagates to those rocks and whatnot. And this is Jasmin and his group did that. And then we recently, about 2, maybe 3 weeks ago at the most, we re-entered that well to try to reopen it with the hope that we can measure deeper. Well, we made it 60 meters deeper than ever because it just, again, overnight it collapsed back. Like this was like they finished drilling at 9 p.m. By 8 a.m. we were back and we were on site to try to measure temperature, and we encountered obstruction at 410. But we got similar results that what was collected last year, which is just slightly above average geothermal gradient at about 30 degrees C per kilometer. Another thing we did, which is more kind of looking forward, we partnered with the Geological Survey of Canada and just completed last week a very extensive regional magnetotelluric survey. So this is much coarser scale than what we've done at community level. But the intent here is to image very large portion of southern Yukon. We have coverage across quite a bit of southern Yukon, pretty much all the roads across southern Yukon. And the idea would be to sort of help us zero in on where the next targeted study should be. Where do we see anomalies in that regional scale level where we could go back and say, okay, now let's do some really detailed work and try to see whether there's opportunity there. This is just that section at the bottom is a quick example of what was acquired last year, right here to Whitehorse. And then we can see some features in there. This has not been analyzed in any extent. So once we start doing more detailed analysis of that data, that those pictures might change. But there are features underneath the Whitehorse area that are worth investigating. That might lead us to a better understanding of where we should go next. So I'm coming to the end here. The other thing that we're doing is just data compilations, just mining old report. There was a number of series over probably about 10 years that were commissioned by Yukon Energy Corporation. They were mostly done by EBA Engineering, Tetra Tech now. And they kind of investigated a bunch of different targets all over Yukon. And we are sort of compiling this into one compendium report, which would be more or less a state of what do we know about, Jarvis River, for example, or some of the other areas that have known indication of heat. We also, it's an ongoing compilation. We'll make all that radiogenic heat data that I've been talking. This is going to be available for anybody to grab from our website. The drill hole information is all going to be there with what we know. Wherever we have water chemistry, which is useful in trying developing, that's all going to be hopefully available in coming months from the YGS website. So where does that bring us? What have we really learned? So one of the top thing right from the get-go when I was putting all this stuff together was just looking at that compilation of well data that is shown here on the map. What's evident, of course, we have a lot of data where those oil and gas sedimentary basins are, and there's some deep well. And you can see, I think everything that's orange and red is kind of like intriguing and worth pursuing. And those are some of the opportunities, some areas where maybe we could have heat to underneath that sedimentary blanket to to generate power. Now, all of these, of course, are Eagle Plain. Well, we can have a big power plant at Eagle Plain, but that's a heck of a way from anything. The Yard Basin is not, the closest is Fort Liard, which is a small community. So these are not practical things. But when you look at this map, there's one basin that's right outside our door where there's a paucity of drill hole, and it's the Whitehorse Trough. So, for Whitehorse, Carcross, Carmax, I think this is something we should put some more work, and Eric has spoken to that effect earlier. We should put some more work, and it's important to note that the most advanced geothermal project, nowhere in Canada are we producing geothermal electricity yet, but there's a number of projects that are trying to advance to that stage. And the most advanced project are at Fort Nelson, Alberta 1. I'm not sure what the community is there, but Alberta, and there's the Deep project in Saskatchewan. And all of them are looking at this hot sedimentary aquifer, deep sedimentary basin system. So there might be opportunity in Yukon, and we still have to get some work done to see what are the true opportunities or not. The other thing, we did this Curry Point depth mapping that's kind of led us to investigate various areas. We collected a bunch of data, whether it's temperature profile, whether it's the seismic data that's shown on some of the posters here. And all the data, I shouldn't say all the data, but a lot of the data we have so far is actually telling us that first order approximation is not too bad. Like we're sort of in the ballpark. What we're finding in actuality is in the ballpark with what we expect. From the Curry Point depth, a lot of southern Yukon, we expect we'd have temperature gradient somewhere between 30 and 50. And the ones I've presented here in the presentation are in that 30 to 49 degrees C. So I think, it's not a bad approximation. Doesn't mean it's going to work everywhere, but at least where we look for it, it's not too bad. Based on that, okay, we're well below that 60 degrees C per kilometer to get to that kind of affordable, shallow kind of heat. So I think the real opportunities, and I think some discussion as we go on this afternoon will highlight that. The real opportunities is heat, and as Carolyn shown, heat is one of our big problems. Power is a big problem because we're all transitioning to EV, and we all have more powerful cell phone and whatnot. So we need electricity, but we also need to offset the diesel that we burn in our houses. So I think I think the key message is that the grand prize is electricity. Where we are at now is zero. And anything in between has the potential to be a win, and it's just a matter of scaling and adapting to what we find the resource can give us. So I think there are opportunities. We've learned that through our experience. We started drilling a little blindly when we went to Takini Hot Spring. Then progressively we start beginning to get smarter by applying all these multiple layer geophysics and integrating the geology. And I think that's really the way forward. And I think what I'd like to see from YGS perspective is that we'll probably bang at your door. Eventually, we'd like to get that kind of level of understanding of geology in the subsurface for every Yukon community, so that we have that baseline, so that when somebody comes in and say, hey, we should drill, then we can be informed as to where we should drill. So I think future direction, while we're starting here in Whitehorse, as I was saying, opportunities to check, go in Mayo. There's a lot of those hot granites right around Mayo, and there is warm water at Mayo, and it has been used in a kind of a low degree district heat in the community in the past. So there's a potential there. The Whitehorse Trough ideas we talked about. Old Crow has all these hot granite. Old Crow is remote. It's going to be complicated, difficult to do much of the work there. And it's one of these areas where the Curry Point depth mapping doesn't seem favorable, but all the granites are near Old Crow, and some of them are within less than 10 kilometers, 5 or 10 kilometers from town. So they could well be underneath the town, the village. So that there might be opportunity to even look for this kind of stuff that far north. The other thing is, are there opportunities to offset some of the costs, whether it's producing electricity for mining project, or even if we can't make electricity, if we can heat all the building infrastructure, that's already offsetting some diesel. It's not, it's not going to solve the energy problem for any upcoming mine, but there might be opportunities. And then we're looking for any opportunities to access any mineral exploration or holes. So we're talking to exploration companies across the territories, and if there's something that's 500 meter and deeper, near vertical, then we'll certainly be interested to have a look at the rocks and measure the temperature in there. One of the objectives we're trying to do, so this is the existing heat flow map of Yukon. If you recall, about an hour ago, I showed the Nevada map. Well, we're really patchy because we have no data, but we're starting to fill some of those gaps with the data that we have. So that area to the west of Whitehorse Trough, we're already working toward kind of starting to fill that map. So, and that will become sort of a template to guide future exploration. And that's it for me. So more or less the same material. There's lots of information, and we're all always available to talk about anything Yukon geology.